types of projects don't go around very often. And when they do, and they're this special, it actually means something. What does it mean? So I understand, and I think we all understand, that this is a singular house, right, amongst billions of houses. But it's not about this specific house. It's about what this specific house teaches us, the development team, but also us, the builders, right? And, you know, I'm standing up here giving this talk, but the two people who are actually building it are in the back, right? So Hugh and Brad, who probably won't stand up, and but we have to realize, and Kristen and Brad, we have to realize that all of these projects, like, we can dream up these amazing projects, but people actually have to build them. And when people have to build them, we have to explain to them what all this means. And so the point of my side of the talk is not to reiterate what they said. It's to talk about the lessons that we're trying to teach and the lessons that we're trying to learn and what we're trying to take from this project into other projects. And that's really what matters. And then talking to all of you, like, I collectively congratulate you guys for getting outside in the rain and culling and listening to us trying to push the envelope, because that's how we make change. It's about talking about these things, about sharing these ideas, about... So this is a passive house. It is going to be an airtight, energy-efficient, highly comfortable house. Both of these are mud houses. So this is the house I built in 2005. And this is the one that we just finished last year. This is 3 times larger than this house. And this is built to almost passive standard, but it didn't have the good windows and it didn't have the extra insulation. And this did. Now every time I stay here, then I go back to here, I'm like, that's it, isn't it? I just done this. I just on better windows. And the point I'm trying to make is that passive houses are different. They feel different. They live differently. This is on a busy street. And when you open the door or open a window, it's like, oh, I'm on a busy street. But when everything's closed up and you get that fresh air, it's a completely different feeling. And I don't think people really understand what these houses can be like. They can be so amazingly cool. It changes your entire understanding of what living in a house is about. Next slide. So this is another one of our projects that's also a passive house. And I mean, this is a standard house. So I strongly believe in what is written up here, which is a code compliant house is the worst house or building you can legally build. I don't think that's something we should endeavor to. Like, I think we should endeavor to do something different. And that's what BABSC is all about, is about sharing in these experiences and supporting each other and helping each other. Because change is hard. Building something like this is hard. And if you haven't done it before, it can be terrifying. Now, I live like, I'm kind of stupid and I just like a risk. And so, like, building something like this was just hella fun. But this project is 80%, it uses 80% less energy than a standard house. It is 2.6% more expensive than a standard custom house. This is not a deal breaker for most people. We have to change how we think about these projects next slide. Now, this is San Bruno. And I'd say a proportion of our projects now are all electric. And I don't like this. Like, this terrifies me. All this terrifies me. We should be building better. Like, I know that the Supreme Court just knocks down the all-electric mandate for cities, but that doesn't mean that we can't have these conversations with our clients, with our architects, all the time. Talk about it all the time. We don't have any of these conversations with gas, combustion. That's one. So, this is a very slide. Okay, so how do I start? So this is AI's version of how do you eat an elephant one bite at a time. Let's leave their elephant bites. Like, I was still understand what AI is thinking, right? And it doesn't need to keep quick memory. So here's the thing. So we builders have been kind of constantly taught that we are supposed to do what the architects and the engineers tell us to do. And an architect the other day told me, he said, you know, Dave, I like the fact that you don't do what every other builder does. You kind of second guess every part of the construction process. And in my opinion, if we want to change how we build and what we build and the impact that we have on the environment, we have to question everything. And it starts, next slide, please. And it starts with a deep collaboration between the builders and the architects and the structure. I couldn't find a square, Anthony. I'm sorry. You got out here. But we have to collaborate with our architects and our structural engineers and our clients, because it's our client's house. And if we don't collaborate, if we don't show our clients why this is important, why this benefits them personally, them globally, the people in the region, we're not going to be able to convince them that this is the best thing. Because if you haven't stayed in the passive house, you don't know what passive house is, right? So we have to do a better job. Being specially green educated doesn't mean anything unless you can sell that idea to your client by listening to your clients, listening to your architects, your structural engineers, and showing them why this is better in flight. And it all starts with having these conversations way before we start construction, way before. Pre-construction. This is pre-construction. This is when the architects and the engineers are doing all the heavy lifting. This should be when your clients are making these decisions. If you do it up here, it's too late. It costs the client too much money. It takes too long. These are two different jobs. This job went through pre-construction. Well, it came out with 95% of decisions made. This project didn't. These spots, this is a calendar time with a workday time. These spots are when we are waiting for client decisions. This is what happens. We need to do a better job of incentivizing our clients and explaining to them why they need to make decisions and better decisions. Next slide. All right, so I'm going to talk a little bit about passive house. I'm going to talk a little bit about living, building, challenge. I actually strongly believe, I'm trained in both of them, I strongly believe in those systems. I don't strongly believe in a rigorous adherence to any one system. I believe that we can build better projects without getting our projects certified and spending this money. I mean, this is serious money. This is money. We could use this money for certification to build better windows or better insulation or better air sealing. We can do this. I'm not saying the certification doesn't have its place. What I'm saying is we need to get out of this adherence to certification, or it doesn't mean anything, and concentrate on what we're actually building. Building better projects is what really matters. And educating our clients. They have options. They have the option of upgrading windows to be better windows. That's what matters, is what we're producing. Because certification is a proof of concept. If your client wants to pay for it, awesome. If you are the client and you want to pay for it, awesome. We're super happy. But we would rather see you do better projects. There's lots and lots of certifications. You can get lots. This is just the certifications for Living Building Challenge, right? Like 5 of them, and this is the hardest standard in the world. This is hard stuff. Should be the goal. The goal should be the best project that your client wants and can afford and wants to live in, and the best of the planet. Next slide. All right, this is my little dinky house. Until you've been in one, you don't really know what it means. Until you've been in a passive house, you don't know. And so I'm just asking you to kind of believe in what I'm saying. Next slide. Passive house, capital P, capital H, is not solar passive or passive solar. It is different. It is solar passive or passive solar with a much better envelope and with a fresh air system, right? It is about an entire organizational structure that basically looks to build a quiet, comfortable, durable, long-lasting, energy-efficient house that provides fresh air and is resilient in fires and smog and all the stuff that attracts us or that attacks us in our air. Next slide. This is basically, I'm not going to get into it really deep, but it's basically about really efficient windows, a really efficient envelope, making sure that you supply fresh air to that house, making sure that you have a ventilation system that transfers air. So a ventilation system can be opening a window. And opening a window is 100% inefficient at retaining hot or cold air depending on the season. But with an HRV, which I'll get to at the end of the talk, it is all about changing out the stale indoor air and bringing in fresh air, but pulling the heat so that you're not essentially opening the window and losing all that conditioned air that you've built. Next slide. So this is the Cereza passive house. One of the most important things about any passive house is a hair barrier. And there's essentially a pencil. We should be able to draw a pencil all the way around your house without ever lifting it up off the page. That's how you get an air seal. This is the waterproofing for the basement. And David mentioned it, or Anthony mentioned it earlier. The site of this house has a high water table. We basically have to build the foundation so that it could float, right? And it's too heavy to float. But it literally could have water on the walls the whole time. We're not allowed to pump it off. All right, thank you, play. I'll be done. So, and we're also looking at upgrading the insulation. Now, this is ICC value, right? This is where this project is. It's not much greater, right? And Ron Berries is building a house with Rob nicely in Carmel that has no exterior rigid insulation on the walls, right? We're not talking tremendously different houses. We're just talking better houses, better windows, better air sealing, more insulation, primarily the lit. Next slide. I hate Title 4. Title 24 is a complete disaster. Yeah. With Title 24 for this project, so that you have 6.11% compliance margin over Title 24 because Title 24 doesn't understand passive house. It happens over and over and over that when we do the Title 24, it doesn't understand what we're building and gives us margins. We're having to do stupid things to get past Title 24. What we should be using, next slide, is something called PHP. PHP is a passive house planning package. It'll give us our loads, tell us how water compliance is. There's a company out of Colorado called EVU who did the training for me and I think most of my people, in fact, all of my people in passive house training. They do something called a boost report. It's like $2,000 or $4,000 that I've remember. That will do the PHP and give you the whole analysis, and I'll show you some of their output later on. It's fantastic, absolutely fantastic. This house performs unbelievably. I'll get to it. So, it is like, this is a dream, right? Like, these are the houses that we want to be building. Next slide, please. All right. So, can we get up and hand out the slides? So, I strongly believe in active learning. And we're going to do something that Bronwyn and John Stewart did a couple months ago. We're actually going to do a little active learning session. So for about the next 6 or 7 minutes, you're going to get a version of this slide. What I want you to do is twofold. You're going to draw it down with the pen on your table. You're going to draw the air barrier. Okay, so that you want to stop air from flowing from outside inside your house. And then you're going to draw the shortest about the line between the outside and inside thermally. So what you're looking for is bypasses of your insulation. Okay, called a thermal bridge. Does everybody understand that? So the reason you're all sitting at tables is so you could talk about it. So let's talk in class. Rather, this is really, really important. This is how you can define and what floors, walls, more foundations that are walls or foundations, or walls that are really important. So in this one, we have it going across the interface. Because is this a basis or is that a crawl space? The basement too is about a wood wall and here we're up with a wood wall or a crawl space, right? So this has to go all the way down into the dirt. And this will at some point connect with the concrete waterproofing down below. And it goes up past this junction. I can tell you from experience, this junction is incredibly difficult to intersect. It always leaks. In a remodel, it's like a total pain. This one, right? This one we're coming up and then we're coming over. Why do we place it here? We place it here because look at this. This is a vaulted ceiling. Okay? And a vaulted ceiling, what do we know about vaulted ceilings when we have the insulation in the roof? We have to protect the underside or that outside of the air barrier from getting cold. Because if moist air travels up through here and hits this membrane, and this is outside, it will condense, water will condense, and all our drain will get wet and rot. So it has to be here. For those of you who said it's going to be up here, you're going to let your membrane get wet from the condensation, and everything below it will rot out. Make sense? The last one, here. There's no, we're depending on this concrete to not crack it and leak air. There is no solution here, except for coming around it. Based on this, we're assuming that this is inside space as well, right? You see the radiant pipes? So we're going to have to come up and come around or come around over here. And you get the underside of the slab over here. So this, if you drew this, that's wrong. We need to come over here and assume that this is more of the human gang. That is right. But I say what's the wrong answer. I give you the wrong answer. I'm trying to show that it would work here. Right? So you have to assume from the drawings, right? Next line by. Look at after it. All right. Who got this? Who got these? So pass it out to people. John, you should have got them in the morning. Down. Okay. So here we have exterior lifted insulation on the foundation. We have a hyper-insulated wall. But we have this little tiny junction right here where heat can come in through the foundation, go through the wood, and then out. Right? So it's bypassed through a tiny little section. It's bypassed the insulation of that area. Right? But architecturally, we can't really, if we carried this insulation up much higher, it would have given us a hump in our wall. Right? So sometimes there's challenges that we're like, how do we do this effectively without changing the architecture? Right? Here, this is a stinker, right? It's a stinker because we have our window, down our structural header, have to have a structural header. We have our blinds pocket inside the wall that gives us a straight shot right through our structural lumber and those blind pockets. Blind pockets are really, really, really hard to get right. If you put a blind in a wall and you don't have exterior rigid insulation that goes over the top of it, right? Then you're going to get thermal bypass. And then really, anytime you have flashing to this is just a super, super difficult variant. It's always hard. And then the last one, we have a thermal bypass right here, right? Pure and simple. So we do have cork insulation, but this is the weakest spot, right? So we have insulation, we insulated this, but we have insulation here, so that insulation without trouble getting through to the basement, but getting upstairs, it only has to go through a half-inch of cork, right? What's the solution to that? Insulating the bottom of this flat.
Fabulous, at least.
Yeah, that's true. Or we'll do that a little bit. What do we use?
Don't do it so.
It's under. We didn't use pellets under the slab. We used pellets on the walls. We could have because it's not structural. But you're ruining my talk. It's the
So fucking, I don't know if you're talking. But we cannot touch that trap. That was it. It's cool.
So actually I drew it on slide before. I drew the insulation under the slab because I didn't verify it. But yeah, so this is hard. This is hard. Like, we have to think about each one of these details, and every time, like I mentioned it earlier, like every job is a prototype. Every job gets a little bit better. Our first pass at house, we struggled mightily. Our second, better. Our third, better. Right? Next slide, please. Don't expect to get everything right the first time. Okay. This is the living building challenge. I love the living building challenge. It's basically impossible for any infill project. To get full living building challenge, you have to be water independent. Forget about it, right? You're not even allowed to collect water in some places. And even if you did, you'd have to move a giant tank underneath your house to collect it all, okay? But there's energy pedals, the carbon pedal, the equity pedal, the beauty pedal, that's architectural design and incorporating the outside of the inside. The materials pedal is all about material densities. I took this training last year. I learned so much about the materiality of the materials that we were using in our houses, to the point where I was surprised that we missed some things. Next slide. So we have an intern who is a fantastic human being earlier this year, and she built, or last year, she built a tool for us to look at all of the materials we're using in our company and see if they had red list chemicals. This is a lot of work. So not only is the tools absolutely awesome, but here, some of this stuff, like so Rust-Oleum, we got all these other products, this Rust-Oleum, like that pops out as high red list chemicals. It's a toxic chemical. One of the most surprising, so for you structural engineers and builders, set epoxy, SET epoxy, which is the epoxy they use to anchor hold downs into concrete. It's like 40 to 60% red list chemical. Think about that. 40 to 60% toxic chemical. And I would talk to Anthony or any of my other structural engineers. I don't know if there's an alternate material. I would love to use another material that doesn't introduce 40 to 60% red list chemicals in our products. And what? Next slide. There are a lot of different certification systems. So we are taking the tool that we had built this summer for red list, and we're pulling out all of these different, the LBD Watch, EPA, the Good House something, Green, Great Good House, or Good Green House, or whatever. Blake Sheldon Tallis, Lead Pilot, Perkins and Will. We're pulling all their databases, and we're aggregating all the chemicals, and then we're basically building a tool to search all of those chemicals, all those different certification systems, just to try to find stuff that maybe doesn't appear on the red list chemical database that does on other ones. It is a lot of work. Somebody the other day goes, why are we responsible for doing this? Nobody else is doing it, right? Like, because there's a need and we need to do it. Next slide. The red list, if you're not familiar, is the Living Building Challenge way to certify materials for toxic chemicals. It's like 21 families, about 11,000 chemicals, and growing every year of toxic chemicals. We can look at us through CAS numbers. That's what the tool does. We have the tool on our website, but I didn't like how it works, so we're going to try to rebuild it and make it easier. Let's put that back up. Next slide. You can also go to websites like Clone Free, like Mindful Materials. These are great websites for looking up materials. Mindful Materials, unfortunately, it's mostly commercial materials. I'm a bit bummed. Clone Free is actually better. They've got a great job. Next slide. They give you basically, you look up a section for composite woods. We give you basically green, which is good, all the way to back for red, which is bad. Very easily. So if you click on this next slide, it'll give you this list. So this green, click on this green, it gives me this, and these are the ones that are actually good for you. So right now, very easily, if you go to this website, say I want to use a paint, well, I can say, oh, Venture War. This paint fits this good green gap category, right? There's resources out there. They don't cover a lot. Next slide. And they require a lot of work. You have to be willing to talk to other people. You have to be willing to share resources. We're trying to aggregate. We're one small company. We're doing everything we can to put this information out there, but it's a lot. But you also have to, to quote Apple, think different. You have to go into every step and question what you're doing and why you're doing it, and if it's the best way. So this is the first time when we went like, why are we using pressure-treated lumber for the retainment for these temporary walls? Yes, so it is. It's called soldier beam shoring. But why are we using pressure-treated lumber? Pressure-treated lumber is so that the lumber doesn't rot out and turn to mulch. No, you're leaving it in the ground. You just basically leave it in the ground and it rots out. You want it to rot out, right? You want this to be just mulch in 10 years, right? And if you put PT in here, then modern-day PTs are water-soluble. So we water-soluble chemicals that we're now putting into an area with a high water table that is basically going to leach out of that wood that's in there for forever, poisoning the ground around this house. We can do better. Like, and this wood is cheaper, right? Like, why did I never think of that before? Like, this is not rocket science. This is just like paying attention to things that we just didn't think about before. Nice life. Here's another one. Everybody knows, or at least if you know, you will right now, PVC is toxic. The manufacture, the disposal, and the burning of PVC produces a chemical called dioxin. Dioxin is the most potent toxins known to man. And we put it thoroughly in our houses in sprinkler systems. And we have water sitting in these sprinkler systems for eons, leaching out the chemicals out of this. What's the alternative to this? Copper systems, right? We have started to introduce copper fire sprinkler systems. It's about a 20% increase in the fire sprinkler system price. Very easily to get rid of a toxic chemical out of our projects without introducing anything except a little bit more investment in a fire sprinkler system, which is already like cheap insurance, right? Just thinking of a little bit different. Next slide. So first we planned, now we built. So what about this project is so amazing, make clay? First of all, deconstruction. This project was, City of Palo Alto requires deconstruction, which means that you don't get to drive an excavator or a bulldozer into the front yard and drive it out the backyard with a dump truck, right? So you have to take it apart piece by piece. There's a lot of materials here that you can recycle. Next slide. The labor to deconstruct costs about twice as much as the labor to demo and the dumping costs, right? So what do we do? How do we make this a better process? So on this project, we have, and we've done it on subsequent projects and previous projects. So what we do is we, first of all, call an appraiser and say, hey, is there anything of value in this house? And if they say yes, then we tag it and we have a deconstruction company pull it, and then we donate it to a deconstruction salvage company, which then gives us a tax break on that material. If the appraiser says no, doesn't give us a tax rate, it's apply the whole order of tax rate. If they say no, then we to call a company called Full House Building Supply. Full House Building Supply will come in and he'll go, yeah, I can do this. And then we'll go around, take pictures, and then we'll have a sale. The orders are out of the house. So they're not coming in while the orders there. No, I want that TV. They're coming in and they're basically buying. They just come in and sell it for fractions of a dollar. All the stuff in the house that anybody wants. You come in, those people take it, they sign a waiver so that you're not liable if they get hurt. And then they take all the stuff, and what you're left with is the stuff that nobody has any value. Now you've reduced, there's value, but not value to anybody in this area. So now you've reduced the amount of deconstruction material you have to take down, and the deconstruction bill goes down, and you've disposed of less. Next slide. So what does that mean? 91% of that house was salvaged or reused. 91%. That's including the foundation. 91%. 9% of that house went into landfill. We took it from 100% into the landfill to 9% into the landfill. That's a freaking good deal for the environment and for the climate and for the population in general. Next slide. So Anthony talked a little bit about it. We have been using a 70% replacement concrete for 15 years, 14 years. This is the recipe. It is not. You guys want a 70% replacement? I'm happy to share this with you. We have 3,000, 3,500, 4,000, 4,500, 5,000 PSI, 70% replacement concrete. It is a little bit more expensive than no replacement concrete. It is a better concrete because it gets stronger over a duration. So next slide, please. This is fly ash. So these are holding, and so you see this right here. This is a coal-fired power plant. And all these bays right here are where the coal plant scrubbed their stacks, pulled out the fly ash, and then stored it in ponds right next to a river. And every once in a while, these ponds break. They flood their fly ash, which is filled with heavy metals, into the waterways and overwhelm houses, right? So selenium, arsenic, boron, They do aluminum, lead, mercury, chromium, radionuclides, uranium, and thorium. Right? Those are heavy metals. Those are not good heavy metals. Next slide, please. So what do? I'm losing it. Slide. Go back. So we take this. I don't know where that slide is. I'll probably get it later. So we take that fly ash, we use it in concrete. And what happens when it gets used in concrete, it offsets cement, and it becomes part of the concrete mix. And what happens to all those heavy metals? They get fixed in the cement. They get fixed in the concrete. This bioavailable heavy metals, that means that if you were exposed to them, you could absorb them, eat them, breathe them in. When it's a part of concrete, they are no longer bioavailable unless you're into eating concrete. Right? Next slide. All right. So I'll read you about it. So first of all, this is a foundation plan that we worked with the architects and the structural engineer. We have an insulation layer going around the entire project. Now, there's a material which I'm going to get to in a bit that we're going to talk about, but this is the option that we came up with for insulating that foundation. So we put 2 inches, I think 2 inches or 4 inches. So 2 inches of polystyrene, a high PSI level polystyrene underneath this foundation, and then the wrap and then quarter waterproofing over that, and then that's the foundation. So now we have an insulated foundation. So now we're up the wall fixed line. So we would like to not use petroleum products for insulation. And so there's this material called Flavel. There's another manufacturer called Hero Aggregates that produce an aerated glass, a recycled glass bar. So essentially take a bunch of recycled bottles, they melt it, they blow a bunch of air in it, and they form essentially these glass aggregates. These glass aggregates, just like petroleum-based foam, have little air bubbles in them. You can see the structure in here in kind of fuzzy. So that actually gives you an insulative value. I think it's about 1.9 for this material. This material is an engineered, designed product, so it's a structural product. This material, unfortunately, is made in Maine. And so for us to use it on our project, we would have to truck it from Maine to California on a truck. And it's not just one truck. I think we counted it was 7 semis. The truck to use this product, right? Urban Chill had a much better idea, right? So we couldn't use, let's go back slide. Okay, this is water. So pumice is not a man-made product. It does not have engineering caps. We cannot put a giant heavy building on top of pumice because we can't make sure that it's not going to give up the goods, right? It's not going to crush at some level, and that's bad. Clients typically like their houses flat. And so what we did is we replaced the aggregate for the rock that we use for the backfill on the house. So instead of going to a mountain, digging up that mountain with all that heavy rock and bringing it truckload by truckload, 7 yards at a time, and dumping it and spraying it around here, and then having it on the outside of the foundation with the insulation, we replaced all but an inch of this insulation. So this insulation is polystyrene insulation. It's here just to protect the membrane of the waterproofing behind it. Remember, this product is basically designed to sit in a giant pond of water with water going way up the wall. That membrane has to be perfect forever. We use a little bit of that foam insulation more as a bumper until we backfill with this rock. This rock has an R value. It's about 10 dollars. Yeah, so one. So we have like 18 inches of rip. So we have an R19 R22 of insulation on the outside. We replaced the heavy rock. We use the pumice to do that. And we've also given the water comes up here, the water replaced the percolate and go down, right? We've taken a natural material and offset it. It's similar to the straw hill and offset what could have been a much more environmentally damaging material called foam. Not very far from here. We actually wanted it at a local. Yes. Yeah. With a landscaping company. So none of we were after bond. Yeah, no, no, recently there's places, there's lava fields all over. Next slide, yes. All right. So if we didn't get to use this, I still want to use this. I have one project where we replace some of the rebar. this is fiberglass rebar. It has a fraction of the embodied carbon of lead rebar. It's a little bit more expensive though. Actually, during the middle of the pandemic, it cost half of the price of iron rebar. The challenge with fiberglass rebar is that it doesn't have the bending resistance. So if you bend it, it can break, whereas iron doesn't break. And we live in earthquake country where everything bends in an earthquake, right? So, we could use it, but it has to be strategically designed. Any amount of offset of iron rebar we should take in life. And next slide. All right. So I would show this to Anthony. So he's just going to have to hold his nose while I talk about this. And all the rest of the structural engineers. So we design houses, or should say, Anthony and the rest of the structural engineers design houses to withstand earthquakes. And when you design the house to withstand earthquakes, you have to design the foundation to specifically design the load of a completed house in an earthquake of a certain size for racking and not falling apart, right? So we have to, the kind of common number is you have 28 days strength. Okay? So these are three. This is standard concrete, less than 35% fly ash and 65 to 35%. So more fly ash. And what do you see? You see that fly ash concrete continues to get stronger and stronger. And actually, even though they have the same 28-day strength, it gets much stronger, 30% more stronger after essentially a year. So can we start looking at our projects not at a 28-day strength? Because you don't build. Anybody else here has built a house? You don't build a house in 28 days, right? Maybe you've gotten some of your framing up, but you're not building a house in 28 days. We have the ability to change how we think about structural engineering, right? About getting a 56-day strength and making sure that that's okay. Next slide. Where did you go at? Sorry? Awesome. So, I thought it was... So this is radon country. We live in fairly medium radon country. All right. Radon is a radioactive gas you get exposed to in any house with a crawl space or a basement. We should use a radon system, even a passive radon system, in every project we build with a basement. You know how they found out what radon was? There's a guy working at there's a guy working at a nuclear power plant, and he went home, and then he came back, and he forgot to take his dose monitor off and leave it at the nuclear power plant. He went home, came back, he lit up. He lit up hot. And they went to his house, and they're like, is he smuggling the radioactive material to his house? Went down to his basement, it was filled with radon, right? Radon causes lung cancer, amongst other cancers. So we could easily just put a pipe into our crawl space, our areas underneath our slabs, and then test it like 6 or 8 months after. There's an easy test for radon. You test it. If you have radon, you put it in an air pump. Essentially, this is a dryer booster there, right? And now you get radon out. We never let sag pressure build up. And if you have a crack in your foundation, you never get radon to your house. It costs almost nothing. The test is like $49. If it comes up positive, you put a booster fan in, that's like $200. And if it comes up negative, then you don't do anything. It costs you $49. Makes sense? Next slide. Framing structure. Next slide. All right. These are advanced framing techniques. If you don't know what these are, this can save you money if you're building a house, if you're designing a house. We replaced this beam. This beam used to be steel. We replaced it with glue lam that fit inside the wall cavity, so we had to have a bigger colored glue lam. But we just built up our floor, so now the panels go across the top of this. This is a moment frame. This moment frame, we work with structural and architectural to vary this in insulation in the wall. So now we don't have steel going from outside the wall to inside the wall. We basically, as much as we could, got rid of the thermal break that is caused by this steel in this wall. This is ladder walking. All this is cut-offs from when they framed the walls. Now we don't have 2 big pieces of wood that form the 2 sides of this perpendicular wall that in an exterior wall would preclude us from insulating that cavity. Yes?
Did you have trouble with building inspectors?
No, never. We've been doing this for 20 years. Yeah. Point board on center framing. In the unburied walls that don't have big old 4x12 headers, right? Like, we can do this by just paying attention to detail. Next line. We don't use any dimensional lumber over 8 inches if we can get away with it. We have to have a conversation with a structural engineer because they have the final say. These are 2 giant beams. This is a beam made of small 8-inch, between 8 and 10-inch trees. This is a beam that has to come out of a tree that's 150 years old. This is old growth. This is trees that reach maturity in 17 years, right? And this is actually, unless this is structural, this is stronger than this standard beam over here. Next slide. Yeah, no shrinkage, exactly right. All right. We're trying to get rid of all toxins in-house. Sounds like a fairly rudimentary kind of conversation, right? Of course we get rid of all toxins out of the house. But what are we putting constantly in houses that bottoms the walls when they touch concrete? Pressure-treated lumber. So we've used TPO. This is a picture of a video, so sorry. This is just a piece of roofing material. We rake it into strips. We put it under the plates. We stopped any water movement from the concrete into the floor. We've gotten rid of all the pressure-treated lumber in our house. Now we don't have to use special hardware that's resistant to the toxin that comes in the pressure-treated lumber. This is essentially free because this wood is cheaper than pressure-treated lumber. Next slide. This used to be a steel beam. We worked with structural engineer to replace it with a wood beam, made it a little bit taller. We're super happy with that because this steel beams, actually 2 steel beams, were in the exterior envelope, which are embedded. We will thermal break. Right? Next slide. Again, the moment frame, thermal breaks. See how this steel beam, we actually have a little bit over on this side. This steel beam is embedded in insulation. No thermal bridge. This right here, this used to be steel, and that used to be steel. We got rid of them and made them wood, working with the structural engineer, the architect, and now we have, it has to be wood. It can't be tall, right? I mean, these are very, very heavy windows. They're 15 feet tall, but we reduced it so now we can do it with wood instead of steel, which is, steel is a conductivity that's 300 times worse than wood, right? Next slide. All right, overframing. The goal of overframing, which is building a roof over the top of your existing. So this is your structural roofs. This is your insulation roof with your roofing material on the top. We make it so that we're basically breaking up the conductivity of structural members through that insulation. This is what it looks like. This is the infill of the rigid foam on the top of the roof. We do this. So now this is the house. The house, this room right here in this house got to 135 degrees in the summertime, right? Now it has an R60 roof. But just having this forward frame insulation on the bottom and the top of it, we dramatically changed. This is our passive house. So you overframe, you fill it with rigid insulation, you put plywood on top, and you put your roofing material. That's it. Now we got the air seal. So this is an air seal that goes all the way around the wall. So the air seal, like we had that before, comes up this wall and over that, and now you have the air seal across your rafters. This is the easiest way to get an incredible house. We've added a lot of insulation to the roof. Next slide. These are the different broke downs. So I am a huge fan of these panels. They are not without challenges. Okay, as everything that we do, there are some challenges. First of all, the floor texture is very heavy. As Anthony was talking about, they're heavy. You have to know that we're you have to test for humidity. Okay, it's not on this slide. They have to be supported on 2 sides by big muffler material. This is Utex, which I'll pop them out in a minute. It takes a little bit of time to anchor this down. You have to train your team next play. What happens if you have the 17th atmospheric river in your house and water is getting in and you can't do anything about it? You have to test for humidity. You have to pull out some straw. We can replace it with more straw. We can replace it with sheep's wool, both equally low embodied carbon. The hold downs. So unfortunately, I don't know if Anthony's used this in this is going to deal with this, but the hold downs are on the outside of the panels. They can't put 4x inside the panel, so you have to add the hold down and then screw the hold down to a 4x that's screwed inside. So the hold downs are outside the panel. This is a window bucker here, and the 4x here is inside for holding that down. So it's a little bit more tricky to do for hold downs for your walls, but if you go in and because we're buried on two different points, that wall is 15 inches thick. Because we're buried into this weight, we have beams. That beam has to be two beams. When we have foundation, oops, I covered it up. Look, that foundation has to accommodate both sides of that panel in order to support that load. I really hope you guys come in April 20th to the house, because we'll have the windows in. I was up in this house the other day, and there's no windows, and the whole front of the house was open. I went into a corner where there's straw panels on both sides. It is wicked quiet. It is, I don't know what it is about the straw. They absorb sound it's like amazing. I can't imagine what this place is going to be like when the windows go in. Next slide. All right. Detailed from that itself. So, next slide. Forest Stewardship Council, FSC, or SFI, Sustainable Forestry Initiative. I'm not going to get into it. There's lots. FSC is the real certification. We buy all of our lumber is FSC certified. SFI, we see all the time. It is developed by the American paper and pulp industry to offset, essentially, the value of FSC. This is essentially VS. Please make your choices wisely. So you have to order ahead for FSC. It is not supplied by everybody. It makes a difference. This is FSC forest. This is SFI certified forest. Right? There's a huge difference, actually. But exterior all open, no quality. All right. You guys remember this about 5 to 6 years ago, right? So I often get people asking me, well, why should I build passive house? My energy bills aren't that big. You're right. You shouldn't build a passive house because you want to save energy. Absolutely not why you should do it, right? You should do it because you don't want your kids reading this. Because if you don't air seal your house, whether it's a remodel or otherwise, your kids and your family and your husbands and wives and parents are reading this, and all of the other stuff that comes in through our windows and our doors and our walls and our floors, everything, right? We will do better with this. Next slide. Okay. This is not something you should aspire to, right? What not to do? Tie back. You see this? This is supposed to be your air seal. They're just putting it across the mob in the wall, right? There's not even caulking or anything there to stop air from leaking right into the house, right? This is a dip hole. For anybody who's ever gone into a house and looked at all the water damage, whether it's your house or a client's house, you know that basically if you have somebody who's right, take care, and these lettuce through the tape. And feel like it just doesn't make any sense. But basically you have this lid, and that lid catches water and will eventually fail. And then what's happening? What's the golden rule about shingling in your houses? Shingle outside. You don't shingle inside, which is what you're doing with your horizontal lines of tape here, right? Just saying no. Next slide. I'm a huge fan of peel and stick waterproofing and air barriers. Why inch stamp? So if I was to come over to this wall, and this is all stuck to the wall. If I was going over one cut right here in the middle of the plywood panel, the only air that would leak out through here is the air from any seams that radiated from that little cut, right? If this was a Tyvek wall, as soon as I penetrated it anywhere, it would run around inside the Tyvek until it hit an opening and go inside the house. This stuff is bomb-proof. It is fantastic. It makes air sealing so much easier. Next slide. It also looks as cool. Right, this is Butex. So Butex is essentially wood fiber. Now, unfortunately, it's made in England right now, and you have to ship it over. Their manufacturers in the United States are making it now. They're not making the forward form of it, but it makes tunnel room. You use it for exterior insulation. It is a fantastic product. We want to start using it all the time. This carbon is originally going to try to use or cork insulation, and then we got a call yesterday that said, oh, sorry, our cork is 4 months backlog. You were supposed to receive it next week, and now it's 4 months backlog, right? So great product as well. Also a super good product for exterior rigid insulation. Don't put it inside your wall cavities. Yes, sir.
Timber HP is now making
Oh, really? Okay.
off the TOD with
And there will be insect scans ever. Okay. Okay. All right. Rain screen. If you're building a house or remodeling your house, you're not putting a rain screen on it, which is basically just a little gap between the siding and the wall. You're doing a huge disservice to you. Basically, once you put your siding on, it's impossible for that water to jump across the inch or half-inch gap and get to your insulation or your wall, the WRB. It falls down, comes out, it's directed outside. This is not, if you're residing your house, this is not a huge ad. This underneath this siding right here, this is the insulation. I put another waterproofing barrier over the top of it. So basically, water would have to be driven by a jet to get into this cavity. This is a forever, right? Next slide. All right, windows are huge. I'm not going to dive too much into it. This is the same price as this. See that this stacks R3, R6. We just got done speccing windows for a project. We had 3 bids for this large project. We had Zola windows, which came in at $350,000. It's a big one. $350,000 for the windows. We had another American manufacturer. So Zolas were R7. Another manufacturer, R3, for $425,000. And another California manufacturer that was $500,000. That was R3. And the client didn't choose the R7 windows because of the settings. We need to do a better job of voicing our frustration to window and door companies on this fairly homogeneous cross-section of passive house windows, right? I've been literally going to the passive house conference that I will talk to you about, and I'm spending the next week and a half going to all the window manufacturers in Europe, telling them that we need a thin sash passive house window because it'd be very popular, because that's what most of our clients want, a thinner sash window.
Still a better design for that style window. You don't need the thin sash. You just need to be more creative at how it's designed. And you can make them look thin if you're smart with your detail. Sorry, put it into a towel.
Yeah, save up for working the trades base of meat. Just David.
Yeah. So, Bronwyn's going to come to all of my future meetings of architects. There we go. Not the fiction out. Next up. All right. These are the windows for this project. They're like an R7 point at the Spetzen, like an R7. For no more than a Colby and Colby window. Right? Like a standard American window. These are freaking crazy amazing. Next slide. Again, you can put these in giant window walls in the snow, and they're triple pane, super quiet, airtight. They have 1/10 of the amount of air infiltration that a standard American style R3 window. A 10, 90% less air infiltration. Next slide. Now, these passive house windows, passive house doors, and also like straw panel doors, it makes difference where you put your window. So most of the windows in American houses are put on the outside of the flange of the window. What sits on the plywood, and then you put your siding on the top of it. This is the delta in temperature between the inside and the outside at the window. 13 degrees versus if you put it in the middle.
Well, I made it numbers at 16.
Starts 16 degrees temperature bit. Anyway, I don't know why the numbers are up. Make a test. There's typically a 6 to 8 degree difference on a thick wall house between windows in the middle of the wall and windows on the inside of the outside or the inside of the wall. I don't know why the numbers should be cut. It's Celsius probably. Next slide. The 2.6. All right. Air sealing and window box. When you have this wall, it is 16 inches thick, right? You can place your window anywhere you want. If the client wants a nice window seat, you can put it to the outside. You take a little bit of the hit in energy efficiency, but now the client has a 12 or 15-inch deep window seat, right? When they get installed, the best thing we can do for them is to flash them really, really well. The absolutely best thing we can do for them is put a roof over the top of them to protect them from the elements, right? Also to shade them in the summer. Next slide. I know this sounds crazy. Flashing material. Flashing material is really important. Flashing material not only directs water away from the window and door openings, but this is a detail that uses a flashing that comes out over the top of the window. This is an incredibly crucial point of any water infiltration process, of getting it right. And if you have that flashing is made out of stainless steel or a highly conductive metal, you actually get a much faster heat transfer through, right? So maybe, we can find other materials. Now, it has to be metal here to resist sun exposure, but we could find other materials or place that flashing in places where we're not conducting a lot of energy through the bolts. So they play. Durability of exterior finishes is one of the most important things. Nobody wants a house that lasts 10 years or 20 years, right? We want a house that lasts forever. Next slide. But we also want to make sure that when we're speccing materials, we're also paying attention to what's in those materials. So we had the original spec for this roofing material, and we did, thankfully, we were doing our red list testing on that process, and we called the manufacturer, because the Living Building Challenge has a threshold of 100 parts per billion, right, per billion. And so we asked the manufacturers for all the materials all the chemicals that were in their roofing material that were above 100 parts per million. And this one came up positive for a chemical called chromium-6. Chromium-6 is what Erin Rokovich sued PG&E for. We found an equivalent material from a different manufacturer that didn't have chromium-6. Same price, same material. This one had an added rust inhibitor. This one didn't. Sometimes we have to do some deep diving to find out what maybe we didn't know originally, right? Next slide. So Nathan already mentioned this. I still love the story of the recycled redwood. The redwood, first of all, is absolutely gorgeous. It comes from a Nike facility. I talk about going from a place of plowshares to wherever. I love it. We have to understand that redwood is not a forever material, right? It will eventually get gray, and if the client is okay with that, awesome. If the client is not okay with that, they have to be okay with maintaining that redwood for the life of the house. Next slide. Comfort. All said. Okay, so shading is something that we don't talk about very often, and I actually find this to be incredibly important. So if we have a house and we're depending on the eaves or some plants like this to block the sun in the summertime, and we're expecting it to come in the wintertime and heat the space, we need to be cognizant that the more energy efficient your house is, the more impact that wintertime sun has on heating that space, right? And we need to understand that in the winter, when the sun is lower, we're actually getting more direct light into the windows than we are if it's at a higher angle. So the sun is actually more warming for the amount of photons that are put out. And so we need to be talking about shading not only in the summertime and the wintertime. How do I know this? My house in Santa Cruz in December 4th got to be 78 degrees at the south facing the rain. I haven't turned the heat on this entire year. It's been between 68 and 70 degrees the entire winter long without the heat on. So it's been fantastic. But 78 degrees in a room is a little too much, right? And so we need to think about shading strategies. If you shade, if you out just your normal glass, you get 80% of the heat coming in. If you shade on the inside, still 50% of the heat comes in. If you shade on the outside, 15% of the heat comes in. There's a big difference between those two as far as thermal comfort. We have to think about that. So how do we do that if we don't want blinds on our walls because they leave a giant thermal ridge in our house? Next slide. We think about SHGC, so solar heat gain coefficient. So in this house, we have specifically really no break place with exterior shades. We have this unbelievable, beautiful channel and blast right over the staircase that illuminates the entire center of the house. It's absolutely gorgeous, but this is kind of a west-facing glass, and this is going to get sun in the summertime. So what if we don't want to put lights or plant a big tree in the middle of it? We can use what's called solar heat gain coefficient. So a low gain glass means a glass that doesn't allow a lot of that infrared light to come into the house. Therefore, it's essentially just like shading the glass without actually shading the glass, right? We need to think about how we use solar heat gain coefficient glass to make our places more efficient. Now, next slide.
We will have a giant fir paradise and lab, but damn it,
Okay. So what does this all mean? So this is that report, that email reporting. Low solar heat gain glass, medium solar heat gain glass, high solar heat gain. So this is going to let a lot of light into the house in the summer, cooling demand, right? So if we get a lot of light into the summer, so this is very good windows and a medium level or a low level of insulation, low level of passive house low, right? If we had high solar heat gain glass, we can get 49% higher efficiency than we want to get for passive house. Sorry, higher energy usage for cooling than we want to get. If we use a low solar heat gain glass, we get 50% less. There's 100% difference between just the SHGC on that glass. So then you're saying, well, what's the impact of winter heating next slide? 16% energy reduction by using solar heating glass, 50%. So there's a 30%, 34% difference in heating demand in the wintertime. Right? Yes.
So, if I following the differentiation of the glass you're talking about, it does change the quality of the light coming in. It does change the ability for plants to grow inside the house, and it does change the perception of looking out through the windows.
It does. So what this is referencing is something called visual transmittance. So as you add a solar heat gain coefficient that is lower, meaning less infrared light gets into the space, you get a reduction in the spectrum of visible light, right? So your windows get a little bit darker. Some artists don't like low gain glass, low solar heat gain coefficient glass. Most people, when this whole house or whole room is in low solar heat gain glass, can't tell the difference. What we tell people in strategic ways is to use low solar heat gain glass where you're getting bombarded by the sun and you don't want to be, and then to get other rooms so you don't have the ability to look at the low solar heat gain glass and high solar heat gain glass in the same room or for the same perspective, then you could use the high solar heat gain glass in other rooms and get that full spectrum. Okay? So we have a slight difference, 34%. So that difference in heating and cooling demands, what does that mean in total energy usage for the year? Next slide. It means that if we use a low solar heat gain glass, 56% less than passive house. 56% less than passive house versus 38% less. So it has a much bigger effect by 20% almost of total energy usage, right? By using those low solar heat gain glass. Now here's the number that's crazy. This number right here, 2450. That is kilowatt hours per year. Okay? So think about it. 2,400 kilowatt hours per year for heating and cooling your house. So what does that mean? That's a very arbitrary number for most people, right? So you can assume that a 400 watt solar panel produces 600 kilowatt hours per year. So divide 2,400 into 600, you get 4 PV panels. So this is the house, not very far from the Cereza house. This right here, those 4 little panels provide enough heat to heat and cool this entire house for an entire year. So all the rest of this can be invested in video games or now, even that long we can't see enough or when like it's a completely different spectrum of thinking, right? And this is the house that's so comfortable. We don't have these giant temperature swings from daylight to nighttime. We have these very small temperature swings because there's not a lot of energy or air leak with light. So it's just almost that next slide. The junior brake heat pumps. This heat pump has the heat pump on the outside, water tank on the inside. So you're pumping heat from outside of the house, putting it inside the house. This heat then gets lost to the house itself. In my house in Santa Cruz, this is the only heat source we've used so far. This is enough to supply heat for a 975 square foot passive house. This is inside the house. It's an entire unit. It basically pulls hot air from inside the house, blows cold air outside the house. It heats the water, then some of the water heat leaves that here. You will not see any temperature differences in this system, and it's not loud, but they do make some noise. Okay? What the biggest problem like this is when you use hot water from a system like this, you are literally pulling heat out of the air inside the house. So this is forms a cooling inside the house. If you have multiple of these inside your house, big house, you've essentially got a cold room. And if your cold room doesn't have ventilation from outside the house, you're going to have condensation issues, right? Next slide. Gray water system. I love gray water. It is a fantastic way to use refuse water that goes down the drains and goes to popular to overwhelm your sewage treatment plant. You can use it to distribute water to your plants anywhere in your yard. Next slide. Okay, if we think about the impact of a normal house and a passive house, this is for this size house. You would need 3 air conditioning units like this to supply cooling, or you have this one. So this house can be addressed with one mini split head for the entire house. One head for the entire house. Now that doesn't distribute around the house, but that's the total load for this entire house. Next slide. And this last slide. HRVs. HRVs are about exchanging that air. This is a whole discussion, but basically this is a lot better than opening your window. And they are quiet. They are not like the heating systems of old, the forced air systems of old. You will never hear this unless you have it boost mode because you're using it as a bath fan or something. Next slide. Consequences. So why do we care about all this? Well, next slide. So there's a lot of learning that goes into these houses, not only in building them, but in living in them. You're going to notice that when you have more people in your house gets warm. Like you literally are like, oh man, it's in the middle of winter time and I have 4 people here, and then now I have to open a window or turn on my heating system because it's warm. You're going to notice that your kids smell a lot more. You're going to notice that ventilation, HRV ventilation, is not just nice, it's necessary. That breathing releases a lot of moisture. When I built my house in Santa Clara 2005, I actually had one HRV to service the entire house. And then my kids, we closed the door to the kids' rooms, and they had the audacity to breathe, and they were making ass sleepy. And so their condensation from their air on like crappy Anderson windows caused condensation on those windows, which leaked out and then caused essentially mildew on the window sashes. So I put another HRV into their rooms just to deal with the moisture from their breathing. It is crazy an airtight house to do. You'll learn about dew point, specifically moisture on not big windows. About building sites, you'll have to know more. And then normal systems. Radiant heating systems, which is this picture. As much as people love radiant heating systems largely are appreciated because they're quiet and because they keep your feet warm. But you can't turn a radiant system up on a house that's efficient because you will put too much heat into the atmosphere and your feet won't get warm. So the set input temperature on these floors is typically like 72 degrees, which is not warm on a barefoot, right? Cooling, cooking, and ventilation. You typically have to have what's called a makeup air system if you have a big rain hood, or if you have 2 rain hoods. Windows are super quiet. It actually makes you a little bit noise sensitive. Like you open a window, like it's really loud inside, and you like to fill your windows. Windows are no longer drafting cold to sit next to, and then the sun in the winter, if you're not shading it, seems really a lot more. If you go outside, it's cold because the ambient temperature is cold. When you go inside, you're like, wow, it's really warm. All right, next slide. It all works. This is all about us working together, right? We have to work together. If we're not going to work together, we're never going to get this stuff done. I learned a tremendous amount about this whole process from David as this team. It has been unbelievable. I would admit that I was embodied carbon agnostic before we started this job. I now am passionate about trying to reduce the embodied carbon. I think that this is an incredible process. This project is fantastic. I really hope you guys all come to the tour on April 20th. And I know he's out here, but I super appreciate the client letting us talk about their house and about walking through this entire process.